on normal distribution and other continuous distribution. Last week we talked about discrete random variable distribution. Okay, we talked about binomial and some other, I think we did some other, right? Oh, any question about the binomial and discrete distribution? Okay, yeah. Well, this is a very important chapter. Perhaps I say that in every chapter. Okay? But as you see here, we're going to talk about normal distribution in this chapter. Right? And normal distribution is, as you know, the most frequently used distribution in the statistics. Okay? So I hope you will pay attention and get a good grasp of the normal distribution. Well, first of all, continuous probability distribution. We're talking about continuous random variable. And you know what continuous random variable is, okay? As opposed to discrete random variable. Okay? So examples are something like weight, height, thickness, time, temperature, or money, right? Amount of money is typically considered continuous. Okay? So you can insert any number between two numbers, right? Because there is no gap between any two numbers, right? All right. Yeah, this is what I mean. These can potentially take on any fraction, number value depending only on the ability to precisely and accurately measure, right? So there is no limit on, not only 1, 2, 3. You can go 1.5. Or if you want, you can go 1.56, and so on. Right? There is no limit in how many digits you can go. Right? There is no discontinuation. It's all continuous. Okay. Okay. More exactly, we're going to start talking about the normal distribution, and here are some characteristics or traits of normal distribution. First of all, it is bell-shaped. Or in other words, sometimes we call it mound shape. Okay? You know mound, pitcher's mound, right? If you go to a baseball stadium, okay? Did you know the ground on which pitcher stands is a little bit higher? I don't know exactly how high. 1 foot? Okay? So there is a little mound, and pitcher stands here and throws to the catcher, right? So that's what we call mound shape. Okay? So we have, if you look at the distribution, well, we didn't exactly talk about the shape or actually this curve. We're going to talk about it in the next slide. Okay? But the distribution is thicker in the middle and thinner towards the end, right? Towards the tails. That's what we call bell-shaped distribution or mound-shaped distribution. Okay? So what that means is there are more observations in the middle compared to the extremes, to the right extremes or left extremes of the distribution. Another important characteristic is symmetry. Okay? The normal distribution is symmetrical, okay? And you know what that is. Okay? And mean, median, and mode are equal. If you have a normal distribution, all three measures of central location are equal value. Okay? And location is determined by mu, or this is Greek letter mu. So it's rather, we indicate the location by Greek letter mu, and we call it mean. Okay? And spread, or the dispersion of the observations, how widely the observations are distributed or scattered. Yeah? And we measure it with the standard deviation, and we use the Greek letter sigma to indicate the standard deviation. So when we try to convey information on any normal distribution, we write it x, any random variable x is distributed normally with the mean and sigma. Okay? So if you write that like this, then something like, say, 150, okay? Then we provided all the necessary information to understand this distribution, okay? So what this means is that the shape of the distribution is normal, okay? And the central location is 100, and the width or spread is 50, how widely those numbers are spread, okay? Okay. The random variable, which is normally distributed, it has infinite theoretical range from positive infinity to negative infinity, right? What that means is when you draw this curve to indicate the normal distribution, you should make sure that this end never touches the ground, okay? If you draw like this, okay, then the distribution ends here and here, right? So that distribution is not infinite, or the range is not infinite, okay? But make sure that the end doesn't touch the ground, which means it just goes on forever, okay? So if you go to extremely large values of x or extremely small values of x, the probability diminishes, okay? In other words, it's highly unlikely that if you have mean value of 100 and the spread of 50, okay, it's highly unlikely that you will find some value like 2.5, 2.5 billion, okay? Extremely large number, or negative 3 billion, right? It's going to be extremely unlikely, but you cannot eliminate the possibility. You cannot ignore the possibility, okay? So make sure you understand that we have unlimited, infinite range. All right. There is one little concept called the normal approximation to the binomial. I know you don't have this in your note. This is just for presentation, okay? So I didn't include this slide in your note because, as you see here, this topic is optional, okay? If you go to the way end, at the end of chapter 6, they have just one line which says section 6.6 online, okay? So that's an additional optional topic. But if you are interested in this topic, after looking at this, you can learn. You can go to this ebook bonus section 6.6. I sent you the link already a few weeks ago, right? You know, when I sent you the link to download data file for edition 7th edition, okay? And if you look at that link, if you want me, I can send you again, right? From that link, you can download this ebook bonus section 6.6, okay? And you can read and learn about it if you like, but you don't have to in this class. That's a little more statistics rather than business statistics, okay? So we don't want to, I'm not going to discuss it in detail. The point is, you have seen this. This is from the slide from previous chapter when we are dealing with binomial distribution, okay? Actual distribution of binomial random variable depends on n and pi, okay? So depending on n, the number of trials and probability of success, in this particular case, the mean value would be 2.5, and standard deviation would come out to be 1.118. And that means if you, let's say, if you throw a coin 100 times, okay, then actual number of heads you're going to get here will be distributed this way. In other words, if you actually calculate using the formula, the binomial formula, this comes out to be 3.125, okay? So out of 100 times, about 31 times, okay, you're going to get the probability that you're going to get 3 heads out of oh well, let's say we're talking about Am I missing something here? Okay. Oh, yeah. We're talking about the different number of trials, okay? Here, so if you have to multiply, this is the case where you throw it 5 times, okay? So if you throw the coin, fair coin, 5 times, okay? Then the probability that you will get 3 heads is about 0.315, and it's equally likely for the 2 heads case, okay? So if you think about 100 times, right, then this distribution will be more like from 0 to 100. Will be more fine. You'll see more bars, okay? So probability that you will get about 49, 50 heads will be a lot more than the extreme case. Okay? So binomial experiment, binomial probability can be approximated by normal distribution. Okay? If you have more trials, okay, something like this, it's gonna be pretty close to normal distribution. Okay? And here's one interesting thing to show you. Let me show you this first. It's a strange name. It's called the quincunx. But this is what. Okay. It's okay. All right. So what this means is we have this 10 rows of pins here, right? And we drop a ball from the top. And ideally, if you do it very exact measurements, right? If you drop your ball right on top, on the center of this pin, then the probability that the ball will drop to the left or right, or left or right, okay, will be equal, right? So probability that it will go right is 1/2. Probability that it will go left is 1/2, right? So that's the first trial, okay? And then the next row is the second trial. So given that the ball dropped to the left or right here, in the next trial, this is another independent trial, right? So there's another half chance and half chance for left and right, okay? So if you do it 10 times, right, then how many balls were we gonna collect on each bin, right? So if you go down here, there are boxes here, or bins here, okay? So this is called the quincunx, or another name is called the Galton's box. Galton's. Francis Galton was another minister, the Reverend. Okay? Last class we talked about the Bayes, Reverend Bayes. Okay? Bayes' theorem was introduced by Reverend Bayes. Okay? And he was a Presbyterian minister, and he, came up with this Bayes' theorem. Okay? Francis Galton was another minister, and his most prominent contribution is regression analysis. Okay? And if you go to your next semester, econometrics, regression analysis will be your primary topic for the entire semester. You'll have to learn about regression analysis. And that was introduced by Francis Galton. Okay? So he was another statistician. Okay? And let's see what happens. Let's continue. Okay. Okay. Well, let's speed it up. All right, you see that distribution at the bottom? Okay. So that's exactly the idea of normal approximation to binomial. Okay. So this is a binomial trial, right? In each trial, you have probability of success. You have only two outcomes, either left or right. Okay. And you're talking about multiple trials. But if you do it many, many times, you will see approximately normal distribution. Okay? So there can be some application of this idea. But again, that's up to you. You don't have to worry about this topic for exam. Okay? Okay. Oops. All right. So now we need to get ourselves familiarized with the term density function. So you can consider this as sort of what? Frequency polygon. You know, in chapter 3, we learned about frequency polygon. And that was if you have a bar chart like this, okay, when you connect the top of all the bars, right, you will have something like this, right, frequency polygon, right? You remember that? Okay. So when you're dealing with this frequency polygon, you have to make sure that each end touches the ground. It is closed, okay? Closed polygon. Okay? But you know, if you have many bars like this, okay, if you connect all the bars on the top, right, that's how we get this kind of curve. Okay, this kind of curve. Okay? And for normal distribution, statisticians actually worked on some ideas, and they came up with the equation of the curve, function of the curve, okay? And came up with this complicated function, okay? You don't have to memorize that, okay? And I'm not going to actually ask you to calculate this function, okay? But I'm just showing you there is such thing, okay? And you know what those are, okay? The natural constant of 2.78 and pi uses all kinds of nasty numbers, okay? And this is the actual functional form of this curve, okay? So that's what we call normal probability density function, okay? So just like binomial probability, we had this situation. Oh, it doesn't. Oh, here. Okay. So here we talked about this probability x, random variable x being certain specific value of x, for example 3. Okay. Given that we have 5 trials and the probability of success in each trial was 0.5, right? So we could write it something like that. X is 2 given number of trials and probability of success. And we could calculate it. You know how to calculate it using the formula or Excel function. Okay? In the normal distribution, okay, we can ask similar question when we have a normal distribution like this, right? And if we have 100 as the mean and the standard deviation of 50, right? What is the chance that when you pick one value at random, that value will be actually 60? Okay? The probability of x being 60. Okay? Well, that's a very easy question to ask. Okay? It is 0. Can you understand why? It has to do with the one concept that we discussed so far, just a few minutes ago. Okay? When you have a continuous distribution like this, right? And when you pick one single value, could be 60 or could be 115 or whatever, right? The probability that the random variable will take that one particular value, single value, is always 0. Why? Well, it has range, but range is infinite, right? The range goes on forever to the positive infinity to negative infinity, right? So there are so many possibilities, infinite possibilities, right? And out of that, it could be 1,000, it could be whatever, when you have a frequency distribution. But what is it? If you have 1,000 divided by infinity, that's 0. Okay? Well, it could be 10 million, but 10 million divided by infinity is still 0. Okay? So if you have a continuous distribution like this, make sure you understand. If you the probability that the random variable will take on any single particular value is always 0. Okay? So then how do we find the probability, normal probability, right? We can only find the probability within a range, not a single particular number, right? So you can ask probability that x will be between 50 and 60. That we can calculate. Or if you want to ask, what is the probability that x will be greater than 60? That we also can calculate, right? Probability that x will be greater than 60. Okay? Yeah, well, we'll talk about it in a few seconds. Yeah. All right. One thing we have to understand about the shape of the normal distribution. Okay? Normal distribution has 3 conditions to satisfy, right? The barrel shape, symmetry, and what? What's the third condition? Barrel shape, symmetric, and, well, that's not really, well, this one, the third condition comes from the symmetrical condition, right? Or, I guess that's another condition, right? Mean and median and mode are equal, right? But there can be thousands and millions of different distributions that satisfy these 3 conditions, right? Some are wide like this pink curve, right? Some may be narrow like this yellow curve. Some may be more in-between type, right? So you can imagine there are thousands of different shapes, right, that can be considered normal, right? Make sure you understand that, right? So some are, wide or fat like this. Some are narrow or sharp like this, okay? So we can think about many different shapes of normal distribution, okay? So it depends on mean and the standard deviation. Again, mean value determines the location, where the distribution is located, okay? And sigma, this determines the spread or width of the distribution. So out of this infinite number of normal distributions, we usually talk about one single specific particular distribution. It's called the standard normal distribution. Standard normal distribution. Okay? Standard normal distribution is just one of the normal distributions with 2 specific values. Okay? Standard normal distribution is the variable which is distributed normally with the mean value of 0 and standard deviation of 1. Okay? Then we say this is a standard normal distribution. Okay? And instead of x, we use z to denote the standard normal variable. I understand that many of you read this jet, but in this class, let's read it like z distribution, x, y, z. Or if you want to pronounce it like Brits or Aussie, maybe you can call it Z, right? Z distribution, but not jet distribution, right? Okay, all right. So this is just the one particular normal distribution which has mean value of 0 and standard deviation of 1. Okay. And from now on, when we are dealing with any normal probability problem, what we need to do is we need to translate that regular normal distribution into standard normal distribution. I'll explain why we do that. You'll see why in a few minutes. Okay? But how do we do that? Well, let's say we have certain distribution here. Okay? Let's make it a little wide. Okay? And the mean value of 100 and the standard deviation is 50. Okay? So in this scale, the 0 will be somewhere here. Okay? Now we need to make or translate this normal distribution into standard normal distribution. Okay? So according to this, the standard normal distribution will be, well, standard normal distribution has a mean value of 0 and standard deviation of 1. So actually, it's going to be very narrow on this scale. Okay? It's going to be a lot taller than this distribution, okay? Because one thing I didn't talk about it when we were discussing probability density function, when you have, if this is a probability density function, then the total area under the curve is 1. Okay? Because what that means is the probability of all possible outcomes, right? So it could be, when you pick a random number out of this random variable x, sometimes you may get very small number, sometimes you get very large number. It is possible, right? But if you add up all possibilities, all those possibilities should be collectively exhaustive and mutually exclusive, okay? So if you add all the probabilities, the total probability or total area under the curve is always 1, okay? So you can have very wide distribution, you can have very narrow distribution, but the total area under the curve must be equal, okay? So if they are narrow, it has to be taller. That's why I drew the curve like this. Anyway, so in order to convert or translate this particular normal distribution into standard normal distribution, first of all, we have to move the distribution towards this way so that it will be centered at 0 instead of 100, right? So that's why we subtract 100 from all x values, right? If you have any x value, like 60 here, right? You have to subtract 100 to bring it, so there's 150, 160 here, right? You have to subtract 100, okay, to bring all the data points this way, right? And then we divide this distance by sigma, okay? Or in this example, there will be 50, okay? Because in this distribution, standard deviation is 50. But in this distribution, standard deviation is 1, right? So what that means is this distribution is 50 times wider than the standard normal distribution. So we have to compress, right? compress the width of all the distribution or the data points, right? The area where all the data points are found, right? And make it comply with the standard deviation of the standardized normal distribution, right? So we divide the distance by 50, right? So that's where this formula came around, okay? Z. If you have any random variable x, which is normal random variable, right? We can convert it into standard normal variable, z, okay? By subtracting the mean value and dividing by sigma, standard deviation, right? So 160, for example, let's say we have x value of 160, right? That's going to be 160 minus 100 divided by 50, right? That's going to be what? 60 divided by 50, which is 1.2, okay? 1.2. Okay? So if you have, well, of course, this is a little too compressed, okay? So let's think about, let's say here's a nice looking standard normal distribution with the mean value of 0 and standard deviation of 1, right? Then this particular value, 160, in this distribution comes to about 1.2, okay? 1.2 in the standard normal distribution. That's the idea of translation of normal into standard normal. Okay? Does it make sense? Okay. Again, why do we do that? Well, I'll tell you in a few minutes. Yeah? But here, before we go on, I think at this point you are ready to understand the meaning of z-score. That's what we call z-score. Okay? If z-score comes out to be 1.2, like this, what's the meaning of it? Can you interpret the meaning of a z-score of 1.2? What can you say? We translated 160 in this particular distribution into standard normal, and the z-score comes out to be 1.2. So what can you say about 160 here? That 160 value is over the mean? What do you mean over the mean? Yes, it is greater than the mean, right? But how far is 160 from the mean? Exactly. Yeah? Right. So if z-score is 1.2, that simply means this particular value, 160, is 1.2 times distance away from the mean. I mean, 1.2 times the standard deviation away from the mean, whatever the standard deviation was. Or in this case, standard deviation was 50, right? So 60 is 1.2 times 50, right? And that's exactly what the z-score is about. You know, this numerator is the distance between the mean, well, we subtract mean from that particular random variable value, right? So this distance or deviation is 1.2 times the sigma, okay? So z-score indicates how many multiples away, how many multiples of the standard deviation away the value is from the mean. Let me see. Z-score indicates how many multiples of the standard deviation away the particular value, let's say the particular value is from the mean. Okay? That's what Z-score is about. Just tells you if the Z-score comes out to be 2.5, that means whatever the number is, it could be 2,500 or whatever, right? Is 2.5 times the standard deviation away from the mean. Okay? Here's an example. Suppose we have a normal distribution with a mean value of 100 and standard deviation of 50. And if you have 200 for that particular x value, right? If the particular x value comes out to be 200 in this normal distribution, we can translate it into z-score by subtracting the mean and dividing the distance by the sigma. Okay? Comes out with 2.0. So what does that mean, 2.0? Well, right here, right? That means that particular value of 200 is 2 standard deviation distance above the mean of 100, above the mean value, right? It can, if it comes out to be -2, right? That simply means it's a 2 standard deviation away below the mean, right? Below the mean value. Okay? So make sure you have clear understanding of the meaning of z value, how to calculate z value. Okay. So another thing we have to clearly understand is regardless of the mean and the standard deviation, we can convert all the numbers into z-score. So this could be original x scale, this could be z scale, right? Which is 0 and 1 scale, where 0 mean value 0 of standard deviation of 1, right? If you want to find out the area under the curve between 100 and 200, right? So this area, okay? That will be exactly the same size as the area between 0 and 2.0 under the standard normal distribution, under the z distribution, right? So regardless of the mean value of any standard deviation of any particular normal distribution, we can find the area or probability, right, by using the z distribution. Okay? This is why we bother to convert or translate the normal variable into z variable, because we know everything about the z distribution. If you, why don't we go to the z table in the back of your chapter, the back of your book. Try to find, I think it's table number E.2. Yes, 724, page number 724. There's table E.2. And if you look at the top of the table, there is something like this. So suppose you're looking for the you converted that particular x value into z-score, and z-score came out to be 0.12. 0.12. Okay? And the original number was 18.6. Okay? And I skipped some examples here, right? But suppose you converted that original x value, it comes out to be 0.12, right? Then, using this table, if you look at the z table, on the first column, you look at the first digit here, below the above the decimal point, right? And it can go in our table from negative 6.0 to negative 0.0. Okay, so in our actual z table, you have to go all the way down to the table, down below at the bottom of the table to see 0.1. Okay. Actually, this table is slightly different from the table in the textbook, right? But so let's say, to make it simple, suppose your z-score is negative 0.12. So we have z-score of negative. Here's 0 and z-score of negative 0.12. Okay. Then the table, the number inside the table gives you this area to the left of that particular number, negative 0.12. Okay. Can someone find it? Negative 0.12. So from the first column, you locate 0.1 or negative 0.1, and then you go across to the second digit below the decimal point, the 0.02, right? What's that number? Negative 0.12. Anybody? 0.4522. Right? Make sure you're able to find that number, 0.4522. It's the second line from the bottom. The last line is negative 0.0, okay? And the second line from the bottom is negative 0.1. So you go to the third column, which is the column for 0.02, right? So this area is 0.4522, right? So we're going to have some exercise on this next class, but the point is the statisticians found out all the necessary numbers, all the possible z values, and calculated the area. And you know how to calculate the area using the probability density function. You use integral calculus, integral calculus, right? So you have this functional form, and the statisticians spend so much time calculating the area below negative 0.002 and so on, right? So we have this compiled table already, right? So we can convert, no matter what x value or the normal distribution we have, we can convert that normal distribution into standard normal, right? And then you can use this table to find the probability, okay? All right, we're going to continue on Thursday.